Today we're going to look at how to create a regression model in Minitab and how to come up with at least a good model, if not the best model. It's very hard to actually know whether you've got the best model or not, but at least there's some steps in Minitab and in other programs too, similar to Minitab, where you can at least come up with a decent model. So we're going to do these steps here in doing regression in Minitab. Let's get a better line there. Okay, so steps in doing regression in Minitab, which would be similar to steps in other programs too. First thing I'm going to do, change the variables if needed. So if you know that ratio variables make sense or squared terms make sense, create those terms. You need to create those. We'll look at that in a second. The first thing we'll start at. And actually, square terms you can actually look for without knowing whether they make sense or not. The other ones you kind of have to know with ratios whether they make sense or not. Then we're going to do something called best subsets. Best subsets is a way in Minitab to take a whole bunch of possible regression models and just come down to 2 or 3 possibly good models. So it kind of makes your job a lot easier. It kind of gets rid of a lot of the useless models and kind of says, okay, these few here look like they might be good. But best subsets only sort of is an overview. It gives you sort of an overview of what might be good models. So really, to see if it's a good model or not, you have to do more of an in-depth check. So you have to check the actual models in more in depth and see if they really are good or not. Then pick the best out of those 2 or 3. And then finally, you can use regression model for prediction if you want to predict future values of y given your x values. So those are the basic steps we're going to go through. I said they're similar to other statistical packages. One thing it might change is other packages may not have best subsets, but there's other things like forward and backward regression where you can kind of do the same type of thing as best subsets. So let's go ahead and scroll down and see the first step here. So here's our example. So again, as we've been using, we're going to be using the states data. Okay, so and our response is going to be verbal. So you want to try and use that as our response, the thing we're trying to get a model for. And we're going to use the average math score, the percent, the dollars spent per student, and the average pay per teacher in the thousands. So remember, verbal, the SAT verbal, that's the average verbal score for the state in 1990. SAT math is the average math score for the state in 1990. Percent was the percent of seniors in the high schools who took the SAT in 1990 in that state. Dollars is just the total dollars spent on the public school system divided by number of students. So it's the cost per student in the school system in 1990. And pay is average teachers pay in thousands in the state. Really here, it doesn't really make sense to use math as a predictor for verbal. The problem is you get math and verbal scores at the same time, right? You give them both the math and verbal at the same time. If for some reason math came before verbal, then it'd be useful. But here, just for purposes of building the model, we'll keep it. But really, if you're really doing this in real life, math wouldn't make sense here. That I can't use that to model verbal because it doesn't happen before it, right? It can't be a cause and effect. There's nothing here. I can't use it for prediction because I won't have the math score for a state before I have a verbal score for the state. But just to kind of show you how we build models, we'll keep it in here. Okay, so the first thing we're going to do is we're first going to create scatter plots. And we're going to do scatter plots of our y, here the verbal, versus each of the x's we started with, each of the predictors. The reason is, if you plot y versus each of the x, you can look for possible square terms. You can see if there are curves in the scatter plots. So squares are the only terms that you can actually visualize, or at least easily visualize. So what I have here are the 4 plots of the verbal versus each of the possible x terms. So just to show you how to do this in Minitab, if you go to Minitab, get up here, I'll just go to Stats. Sorry, just go to Graph, Scatter Plots, Simple. And I did this earlier, so it may still be in there. So I would just do, I probably should take these out because I did it earlier just to check to make sure it'll work, right? Gotta do that. So you put the verbal versus each of your X terms. So verbal versus math, and verbal versus percent, verbal versus dollars, and verbal versus pay. And you get those 4 plots. Okay, you get all 4 plots. And all I've done is I've made these 4 plots smaller and stuck them on the handout here. So here are the 4 plots. So here's verbal, I think you see it, verbal versus the math, verbal versus percent, verbal versus dollars, and verbal versus pay. So what we're looking for here is curves. Well, if you look at this, it's pretty obvious for math, it's just a straight line, right? For math, there's no curve. It's pretty obviously a strong straight line. That strong straight line also tells you math is going to be an important variable when trying to predict verbal. There's a very strong relationship there. As we saw with percent, a curve seemed to make sense. Ooh, it's a little bit high there. So you want to add a percent squared term to our model and try that. With the other two, it's not so obvious. If you look here, it's kind of got this sort of spreading out through these outliers over here. Here, because of those outliers, there may be a curve. It's not obvious. So here, a dollar squared term might be useful. Likewise, here it's not obvious. Here it seems like it's pretty straight, but these ones out here may be a slight curve to it. So again, maybe a curve. So you may want a pay squared term. The only one that's obvious is percent. Percent's the one you definitely want to square. Dollars and pay, it turns out with Minitab, if you square them, it doesn't hurt. If they're not useful, Minitab will throw them out. So if you think that there might be a square term, it's best to try it. Because if it's not useful, the best subsets, when we do the best subsets, we'll take care of that. Here, like I said, that is not obvious. So if you add a square term for dollars and pay, it doesn't really matter. But just to kind of show you how it works, I'm going to add square terms to those. Because if they're not useful, I'll throw them out. But percent squared, that seems to be useful. That's definitely a curve there. So what you need to do now, like it tells up here, use calculator to create these terms. So I need to create a percent squared term, a dollar squared term, and a pay squared term. If I thought ratio terms or interaction terms or log terms were useful, I would create them here too using calculator. So I'll just briefly mention that when we go to Minitab here, and we'll look at that. So what I do is I go to calculator, and now I got to pick an empty column here. So maybe I'll say we've got what, C14 open. So C14, I'm going to take here, I want percent squared. So I'm going to take percent times percent. That's going to be percent squared. If we wanted an interaction term like percent times dollar, I could do percent times dollars here. Or if we wanted to do a ratio term, I could do percent, then divide it by dollars, make a ratio term. And over here you got your functions, so you can do sines and exponentials and logs and everything over here. So you can create any term you want using calculator. You just have to store it in separate columns. So I'll click OK here. And now I'll just close these plots so you can see the data. So let's get it up a little bit. Actually, let's get this up a little bit here. Make this, there we go. So here's C14. So that's percent squared. So I'm going to call it PRCNT2, shorthand for percent squared. And while I'm here, I'm going to name the other columns too. C15, I need, what do I need? I need my dollar squared. So I call that DLRS2. And I need a pay squared. So I call that pay2. So that's where the dollars, so C15 is where the dollar squared is going to go. C16 is where the pay squared is going to go. And I said if I wanted interaction terms, ratio terms, I'd put those in other columns here too. I could create those. So let's go to calculator. I want to do dollar squared now. So in C15, I want dollars. So first, let's get rid of that. I want dollars times dollars. So dollars squared is going to be in the dollars too. So that's my dollars squared. And now calculator. Okay, get rid of these ones. So now in pay2, I want pay times pay. So pay times pay. And obviously I want to cube something, I could do pay times pay times pay, make it pay cubed. I want a cube term. But here we didn't see any cubes, right? Cubes you can also see, right, in the scatter plots, if it kind of bends twice. If it bends 4 times, if it bends 3 times, then it tells you might want to have a fourth term here, like pay times pay times pay times pay. But those are very hard to see. Click OK. So I've now created those 3. Got these 3 new columns, my squared terms. Okay, so let's go back to our handout. Okay, so I've created those terms now. So next step says use stat regression best subsets. What you're going to get is something like this here. So I'm going to show you how to use stat regression best subsets. So what you do here is in stat regression subsets, you put all the possible x terms in. So here we have, what do we have? We have ST math, we have percent, we have dollars, we have pay, and we also have our squared terms. We have percent squared, we have dollars squared, and we have pay squared. So here we have, what is it, 1, 2, 3, 4, 5, 6, 7 possible x terms. So I'll show you how to do that. So go to stat, regression, then best subsets. And what's our response? Our response to our y is the verbal, right? Now you've got 2 choices. You've got these free predictors, or you've got predictors in all models. So if you know a term has to go in the model, so from experience, say this term, if I'm looking, for example, if I'm looking at college GPA, I know high school GPA is going to give me some information. High school GPA has to be in the model. Then I put it in this part down here where it says predictors in all models. It will force that x to be in every model. If you're not sure what x's need to be in the model, what predictors need to be in the model, you just put in the free predictors. That means Minitab's going to take them in and out, play around with them, and see if they need to be in the model or not. So right now, I'm just going to say put all 7 in the free predictors. I don't know which ones have to be in, but visually I know it's probably math going to be in there. So there they are: math, percent, dollars, pay, percent squared, dollars squared, pay squared. If I just clicked OK now, which is fine, Minitab will give me the best models it can, the best 2 models it can of each size. So it would give me the best 2 models with only one x in there, which would be a straight line. it would get, well, as long as the squared terms aren't in there. Then it give me the best two models with two terms in there. But I'm going to change it so it only gives me the best model. So models of each size to print, only going to give me the best one. You do want to fit intercept. That's the A term, the constant. There are reasons, if you know time series and stuff like that, when the intercept doesn't make sense, but for basics stuff, you always want the intercept, so don't uncheck that. If you click OK, it gives us this little table here. And this table here is the same one on your handout. So let's just go to a handout and see what this table shows us. So here's what it gave us. So our response, our y, is up here, right? Here's our y. Here, maybe I should change the color. These are possible x's, right? ST math, percent, dollars, pay, percent squared, dollars squared, pay squared. So notice here, if there are 7 possible x terms, how many different models, so how many different regression models could we create? So in other words, I could have verbal with math and percent in the model, verbal with math and dollars in the model, verbal with just percent in the model, verbal with percent and percent squared in the model, and so on. So the thing here, each x term can be either in or out. Right? It can either be in the model, not in the model. So there are two ways it could be. So each term, there are two things it could be, either in the model, out the model. How many x terms do I have here? Well, there are 7. So there are 2 to the 7th possible models. So if you take 2 raised to the 7th power, that gives you 128. There are 128 here possible different models. That's a lot, right? 128. You want to look at all those 128 models. Actually, we have 127, 2 to the 7th minus 1, possible useful models. Well, why did I take one out here? Well, the one I took out was the one with no terms. If there are no terms, that is when the model is y is equal to average, the r squared is 0. That's not useful if there are no terms in the model. So I took that one where there are no x's in the model out, where the r squared was 0. Tells you nothing. So so in general, there are going to be 2 to the number x terms minus 1 possible useful models. Okay, so here we had 128. So we've gone from 128 possible models. Minitab has reduced it here to 7. So that's nice, right? We've gone from 127 models. So here we've gone from 127 models to 7 models. That makes our life a lot easier. So that's what best subsets is good for. Kind of cleaning things up and looking at what models really might be useful here. Now, what do we look at if we're going to try and find, how do we use this, try and find what is possibly the best model here? Well, first thing is we can't use r squared itself, right? Because r squared increases as you add more x terms. It's good for interpretation, right? It's telling us the percent of the variation in the y in our verbal explained by the model. But as far as getting a good model itself, it's not good for that, because as you add more terms, it has to increase. These values here are increasing. 92.6, 93.6, 94.6. These ones look the same, but actually they're not. This 95.2 is actually slightly bigger than this 95.2. This 95.2 is bigger than that one. If you go out decimal places, so if you have more than just the 0.2, if you get more decimal places, you can show it's actually getting bigger. So that we can't use. What we can use is R squared adjusted. So R squared adjusted penalizes you that's not very good. Penalizes. Penalizes you if you have too many x terms in the model. So that's what's called R squared adjusted. That's just, it takes out what it does is actually takes out a percentage, and the percentage gets bigger each time as you add more terms. So in general, a big R squared adjusted indicates a good model. So we look where R squared adjusted is the biggest here. So here, it looks like the biggest value is 94.6. So it's telling aha, that model might be good. So that's one indication. One thing to note that the R squared adjusted also goes always straight along with the smallest s. So here S is just some measure of the standard deviation, right? So small s, big R squared adjusted. Those always go hand in hand. So that's one thing you can look at, the R squared adjusted or the S, which like I said, they kind of tell you the same thing. The other thing you can look at to try and get a good model, let's see what would be a good color here. We got the green, I guess I can do the purple. Is mallow CP. Okay, mallow CP, it's a fancy formula, and again it's going to penalize you if you have too many terms in the model. But mallow CP, I guess the way to just talk about it is when mallow CP is closest to the number of variables, that indicates a possibly a good model. We're not going to get the details of it. If you want to look at it, you can come to my office and we can talk about it. But it's a fancy formula. It's not as straightforward as the R squared adjusted. So where mallow CP is closest to the number of variables, it indicates a good model. So in other words, you want to look for the minimum of the absolute value of the number of variables minus mallow CP. So if you look here, both with 6 minus 6 is 0, right? An absolute value. And with 4 minus 4, an absolute value, is 0. It's not always 0, but here we've got 2 where it's 0. The other ones aren't 0, at 19.3 and 1, going to give you a difference of 18, 2 and 12.1 give you a difference of 10.1, 3 and 5 give you a difference of 2, 5 and 4.1 gives a difference of 9, 7 and 8 give a difference of 1. So here, those two are the best ones. So here I guess I need more space, so I have to scroll down. So it says here, we can say from R squared adjusted, the model with 5 terms or 5 variables looks good, right? That's what we had here, the 5, the 94.6, because the 94.6 was the highest. From mallow CP, so from mallow CP, pretty ugly mallows. The models with 4 and 6 variables looked good. Since both had the absolute value of the number of variables minus mallow CP equal to 0. They're both the smallest. It says not always 0, but here we had 2, which was 0. So from analyzing this, we have 3 possible models. The one with 5 variables, the one with 4 variables, and the one with 6 variables. So which do we look at first? Well, the answer, what was the overriding principle for regression? Well, the overriding principle is KISS, right? Keep it simple. So the KISS principle tells us when you pick the smallest. So pick the smallest of the possibly good models. So here, it's ugly models. Let's get a better model there. Pick the smallest of possibly good models. So that means we're going to pick the one with 4 variables. And what variables are those? Well, if you go back up, we can see these x's show which terms are in the model, which terms aren't in the model. So for example, with one variable, as it made sense from the scatter plots, that says use just math. If you have 2 variables, it's telling us to use math and pay. If you're using 3 variables, it says to use math, percent squared. So notice pay went out, percent and percent squared came in. And now with 4 variables, pay comes back in. So it's math, percent, pay, percent squared. So that's what we're going to try first. So you want SAT math, we want percent, we want pay, and we want percent squared. Those are the terms we're going to use. Now we want to take this model with the 4 possible x terms and actually look at it in more detail, because the best subset just gives us a general overview. We need to look in more detail to see if there are any actual particular problems with it. What's good about it, what's bad about it. So here, we're going to have to do stat regression. Stat regression will actually let us fit the model get the equation for the model, which is right here, and actually do some tests on that equation and see if it seems like a good model or not. So first again, what I'll do is I'll do stat regression in Minitab, get the same information we have on the handout, and then we'll come back to the handout. So using Minitab, we wanted this model here with the 4 variables, right? We wanted the math, percent, pay, percent squared. So I now go to stat regression. And now I can actually fit the model, and what I'm going to do is I can see how good it is, and I can look at the residuals. The residuals are the leftover distances, those things unexplained, and we'll use those as part of our analysis of the model, see if it's good or not. We need to analyze the residuals. So my response is verbal, my predictors are math, percent, pay, and percent squared. And under graphs, to make it like the other one, we'll do all 4 graphs. As far as residuals, when those are leftover distances, regular is fine, but usually people use standardized. Standardized just makes them the mean 0 and the standard deviation equal to 1. So, because one of the things you're going to check here is normality. So people like that as far as the normality goes. It makes it easier to see if they look normal or not. So you don't have to, but usually people make them standardized residuals. Make the mean of the residual 0, the standard deviation of the residuals 1. Just sort of reformat them. Click OK. OK. We get the 4 graphs, and we get, though it's hard to see now, I get a bunch of information too. We get the model and a bunch of information up here on the session window, which is actually the same with the stuff we have on the handout. So this is the information you have here. So here is your model right here, the regression equation. So here's our model right here, our equation. Verbal is 150, that's our intercept, our A value, plus 0.226 times math, minus 1.07 times percent, minus 0.468 times pay, plus 0.0117 times percent squared. So can you visualize that? Well, let's think about this. Percent and percent squared are really the same variable, right? It's just adding a curve. So percent is one variable with percent squared. Pay is another variable. Mass is another variable. Verbal is another variable. So really you have 4 different variables here. Well, I can't graph in 4 dimensions, so it's something in 4-dimensional space, so you can't actually see this thing. Okay, so that's the actual model though, but you can't really see it. What do we check? Well, the first thing we check, so our first check are the p-values. So these p's here are p-values. Well, what are they doing? Well, if it's a p-value, we're testing something. So here we have tests. The null hypothesis is that the coefficient is 0. The alternative is the coefficient is not 0. So what we're doing here is, for example, we've got this. Here's the first coefficient. The first coefficient. So here are coefficients, right? So the first coefficient is about 150. So this is actually 150. Just a little more exact. This 150 is really 149.66, but really these are the same value. And we're checking, could that value really be 0? Well, if the p-value is less than equal to our usual value of 5%, then HA is true, which says the coefficient is definitely not 0. In other words, that term is useful. If, that's not ugly if, there we go, if the p-value is bigger than 5%, h naught, the coefficient equals 0, could be true. I'm not saying it is true, but it could be true. Which says maybe we don't need that term. So if you look here, what we have. So as far as the constant goes, usually you ignore the constant because you're going to keep it in anyway, whether the p-value is big or small. But the p-value is small, which tells us, aha, that 149.6 is that 150, that's definitely not 0. I want that term. For the math, the 0.662, 0.6619 here, the second value. Right, so this one is the same thing as this one. The p-value is again very small. When it says 0, 0, 0, that means it's less than 0.0005, because it'll round it down. Doesn't mean it's 0, but it means it's very small. So again, it's smaller than 5%, we're okay. For percent, the coefficient is negative 1.07. Again, the p-value is less than 5%, we're okay. But with pay, notice pay is bigger than 5%. Percent squared is again small. So here, this is telling us maybe we don't need pay in the model. Since its p-value is greater than the 5%. It's about 8.5% here. So it's not telling us we have to take it out, but it's telling us, well, maybe that coefficient there could be 0. Maybe this value of negative 4.676, I could just change to 0. That's what it's telling us. So that's the first thing you look at. Look at the p-values. Are any p-values big? If any p-values are big, ignoring the coefficient, don't really worry about that, then maybe those terms don't need to be in the model. That's the first check. The second check is down here. So the second check is just the unusual observations. Fewer unusual observations is better. So here I have nothing to compare to yet, but here we have 2. So here we have 2. So it's 51 observations. Remember, we have got 50 states plus the District of Columbia. 2 isn't bad, but we'll just keep a note of that. We have 2 here. And then when you compare it to another model, we can see how many the other model has. And notice, if we want to, we can figure out what ones they are. That these are observation numbers 2 and 12. And if you go back to the actual data, let's see if I can get the actual data up here. Who were 2 and 12? Ooh, there we go. 2 was Alaska, and 12 was Hawaii, which kind of makes sense, right? Those 2 might be a little different, Alaska and Hawaii, because their cost of living is different and so on, and it's different populations. So maybe that makes sense. Those 2 are out there. The 2 and 12 are kind of unusual. The last 2 checks have to deal with the plots. So here we have 4 plots. So the first 2 plots, we're looking at the residuals versus order, or residuals versus fitted values. So I guess what I'll have to do is I'll have to scroll down a bit. So the third check is to see if do the residuals look random. Because the residuals should be just leftover noise, unexplained stuff, right? Do the residuals look random? So here we'll look at those first two plots, which are the residuals versus order and residuals versus fitted values. So we're going to look at the plots, residuals versus the order, and residuals versus fitted values. What we're looking for there, we want no patterns. And what patterns do we usually look for? So the patterns we usually look for, the ones that usually show up are sort of a curve. You might see a curve either that way or this way, which says you're probably missing a squared x term. One of your predictors needs to be squared. The other pattern you sometimes see is more of a fanning out. And this is usually in the residuals versus the fitted. The fanning out is just a natural product of some variables. For example, say you're looking at income. Say you're looking at income versus age. So suppose this here is age. My y here is income. I might expect some fanning out here. The residuals getting bigger, getting more spread out as age increases. Because here, younger people or younger people's incomes are closer to one another's. As people get older, their incomes diverge or break apart more. So example, you guys, probably your incomes aren't that much different from each other, but as you get older, get to my age, there's a much bigger range as far as incomes go. It's a natural phenomenon. With some things, you expect this fanning out. But the problem is that's bad for regression. You don't want fanning out. It's nothing necessarily bad in the data, it's just the way the data is. Some things actually, you expect to see that. So here, a trick to stop the fanning is to take the natural log of y and redo the regression. You can also take square root of y, but natural log is the main one people do. So there's a log relationship. What happens when you do that, now when you look at natural log of y, it should now be kind of it's more evenly spread out as far as it's not the fanning anymore. What happens, natural log will make the small values spread out more and the big values clump more. So it kind of gets rid of the fanning. It's just a trick because you don't want the fanning. It's bad for prediction. So that's what you do if you see the fanning. So if you look at our data here, do we have either of those? If you look at this first one, there's no curve, no obvious curve here. These two make sense. Those are our unusual observations. So those make sense. I'm going to have two weird ones. So those make sense. Those are my 2 and 12. But otherwise, there's no curve here. Over here, again, I have my two unusual observations. The positions change because now they're versus the fitted values, the approximations of the y values. But again, I have two unusual observations, which makes sense. But otherwise, if you look at it, there's no curve. There's no fanning out. So here, for this third check, for randomness, so residuals randomness, we're okay here. Oop, it's an ugly okay. There we go. So as far as the residuals randomness, we're okay here. The fourth check, I gave you two plots, but actually you only need one of them. The fourth check is, do the residuals have a normal distribution? Right, kind of a bell shape. We expect that to be true. If they're really random, we expect them to have a bell shape. The reason is, if you know Plinko, or it's really called a Galton board, where you have the pegs, right, and the balls bounce down the pegs. That's what randomness should be. It should be like balls bouncing down these Plinko pegs. And what should happen is, if you do this enough times, you should start to get a bell. If it's tall enough, you should start to get some kind of a bell shape at the bottom, as far as where they fall. Because randomness is like all these small variations. I go this way, that way, this way, that way. And if you had enough of these small variations, it should give you kind of a bell shape or normal distribution. That's kind of what we're looking for here. So what we have here, this one I don't use too much. This one, it says it's close to normal if the points are close to the blue line. It's called a ZZ plot, but unless it's really awful, you kind of see it close to the line. And here are two unusual observations. You can't expect those. The best thing, just look at the histogram. Again, we've got our two unusual observations. So you have the two unusual observations. So that's okay. But now if we look at this, the rest of it does look kind of bell. And here, if you look at it, it looks like it's slightly skewed left. May not be that bell. So I may have a problem here with the fourth one, maybe a little bit skewed. So maybe not quite normal. So the fourth check, so that fourth check, our data is slightly skewed left. So maybe a problem with normality. So that's our first model, right? This is the model of, go back up here, using the four variables, the math, percent, pay, percent squared. So now what I want to do is I want to compare this to another model and see which is the better of the two. So now the question is here, so I want to compare this to another model. Which model, there's some weird things there, let's erase that. Which model do I use? Well, it depends on the p-values. If all the p-values are small enough, if less than 0.05, that means all the terms are good, right? Or they seem to be good. Then you want to, so if all the p-values are okay, they're less than 0.05, then you want to try another x, add another predictor. But if any of your p-values are bad, if they're not all less than 5%, which here that's what the case we have, then you probably want to try one fewer predictor. So the p-values tell you which way to go. So remember, with our data, we had a bad p-value here. So rather than going, so since we're looking at 4 variables, we're now going to go to the model with 3 variables. If all these p-values are okay, we'd add a term. We'd go from 4 variables to 5 variables. If I had 2 of these p-values bad, you don't throw both out, because there's something called collinearity, which what may happen is that 2 variables may be giving the same information about y, 2 of the x's, and if you throw one of them out, it makes the other one good, because what's happening is they're kind of splitting their power between them, and they both look like they might be bad, but if you throw one out, then the other one might now become good. So don't just throw out which ones are bad, go back to best subsets and see the best model in best subsets. So what I do now is I go back to best subsets and pick the model with 3 from best subsets, which was math, percent squared, which happens to be pay leaving. So it happens that in this case pay is the one that goes out. So if you scroll down, so get this model from, as it says, best subsets. So don't forget, get it from best subsets. Don't just throw out a bad term from the p-values. Go the best subsets. And here it is. So again, I could do the same. I guess I'll show you. All I need to do is go back here, go to stats, regression, go up here, take out pay, redo it. It redoes the model, but now without pay. That's what I have down here in your handout. So here's the model now without pay in it. So verbal is 154 plus 0.632 times the math score, average score, minus 1.24 times percent plus 0.125 times percent squared, 0.015 times percent squared. So this I could actually probably visualize. It's kind of hard to do because here it's really 3 dimensions, right? I have percent squared go on that axis. It just means that I have a squared term there. I have math, and I have the verbal. So here it's 3-dimensional, so maybe I could plot this thing, but it's kind of nasty. So don't try and do that, but you could, I guess, if you wanted to. So let's look at our checks here. Our first check, all the p-values are okay. So all the p-values less than or equal to 5%. So that's okay. All the terms look good. Second check, only one unusual observation. And here it's 12, right? So that's Hawaii. So Alaska now is an unusual, only Hawaii is unusual. Now our plots. So our third check. Here there's the unusual observation, so we can ignore that. We expect to be there. Here I don't see a curve. Here I don't see a curve. There's no curve. There's no obvious fanning out. It looks like it might start fanning out, but then it stops, right? It's just these ones here are kind of clustered, but otherwise it's not really the fanning out here. It's to get bigger, so no fanning. So the third check's okay. They look random. And now with our fourth check, again we ignore this one. But here's our unusual observation, which we expect. We know it's going to be somewhere. But now if we look at the rest of the data, and it looks closer to bell shape. I mean, it's not too far off. So the fourth check looks okay because it's close to bell shaped. So that's what the results we get for this second model. So now I want to pick the best regression model. Well, here, easy way to do it is just do the 4 checks, right? We have the model with our 4 x terms. We had the model with 3 x terms. And now if we look at the checks, I guess I'll put it on the other side over here. I guess I'm more room over here. Not very good at drawing straight lines. Need to practice that. So 1, 2, 3, and then the bottom will be down here. Okay, so the first check, the p-values. Here we had 1 bad, and here had all okay. With the second check, which was unusual observations, here we had 2, here we had 1. With the third check, randomness, they're both okay. And with the fourth check, the normality or bell-shaped, this was skewed left. Not awful, but a bit skewed left. This was okay. So it looks like, if you just do a little count up here, the model of 3 variables won the first check, won the second check. It was kind of push on the third check, but it won the last check as well. So since the model with 3 x terms won most of the checks, it is the better model. I haven't really proved it's the best model overall, but from using Minitab, it's at least a decent model. It's not overfitted, and it seems to have these good checks of randomness and so on with the residuals. So it seems like the reason why I want randomness in the residuals is because they're not random. It's really telling you probably missing a next term, because you can predict, you can say what's causing it. But if you look random, then you probably got all the terms, all the important terms in your model. Okay, so since one with 3 terms, one we're going to use it. If you are not sure of which model to use, remember KISS. use the smaller model. So here, even if they won 2 each or something, or one another one that the other two kind of pushes, I would go with the model 3 terms. It's only if it's obviously the model with 4 terms is better, I'd pick the bigger model, the one with 4 terms. Okay, so that is our check here as far as which model is best. Using the regression model for prediction. Okay, so now what's our model? So let's go and get our model. So our model, go back up here, is this thing here, right? So so here's our regression equation here. Let's see if it'll let me just copy that. Let's see. Once you just take the whole thing here. I guess I'll get it from the mini tab. Here it is. So I'll copy this, get our regression model down here. There it is. Let's get it up. There's a regression model. That's the one with 4 terms. Sorry, it's the one with 3 terms. Whoop. There we go. Okay. And actually what I'll do is I'll see if I can, since it's doing some weird things here, see if I can get rid of these things. And I get back up here. There we go. So I want to use the model for prediction. So here doesn't make sense because there are no new states, right? There are only 50 states plus District of Columbia. But let's say, use a pen here. Suppose there was a new state, maybe Puerto Rico became a state or something. And let's say 20% of high school seniors took the SAT, and we know the state's average SAT math score is, let's say, 520. Predict the state's average SAT verbal score. So the only thing you have to worry about here is scaling. What scale are your variables on? Well, we know from our data itself. Let's see what the data is. Here we go. So you know from the data itself that both the math scores and verbal scores are in the whole numbers. So I can put the 520 as it is. The thing you have to be careful about is percent. Is percent integer values or is it point something? Well, here it's integer values. So that means when I do my model, when I use this, percents are just the integer values, so are the math. So my prediction is ST verbal is 154 plus 0.632. The ST math was 520 minus 1.24, percent was 20 plus 0.0125, and now I want percent squared, so I want 20 squared or 400. So I just need to calculate that value. So I'm going to take 20 squared or 400 times the 0.0125, which is 5, minus 1.24 times 20, plus 0.632 0.632 times 520 plus 154. So it looks like if I did it correctly, which hopefully I did, the ST verbal is 462.84. So about 463 points is my guess. So that's easy enough prediction. Just stick the numbers in just to make sure that's on the right scale. But probably something you should ask with this, and I may ask in a test, is how confident are you with your prediction? Well, there are two things we can look at. One thing is R squared, right? R squared gives us how well the data fit the model, right? That's one thing R squared does. So if we go back up, what was R squared? So R squared here was 94.6%, which is very high, right? So that's good. So it means the data is very close to the model. So here, since R squared is high, R squared was what, 0.946. 94.6% of the variation or differences in the Y, the ST verbal, is explained by the model. Or the equation. The prediction seems good. So that's one check. So R squared says, yeah, we've got a high R squared, probably this is a good prediction. But there's one more thing we need to check here, which he mentioned early on in regression. Remember, the regression model is only really good inside the range of the original X values. So what I have to do is I have to look at the range. So I need to get the range for the math scores. I need to look at the range of the percent scores. Right, because those ones I'm using in my model. I'm using math and percent in my model. And I want to check to make sure the percent for my new state and the math score for my new state fall inside the range of the original data. If they don't, I don't know if the model holds out there. Remember, like when you talked about the verbal scores versus percents, if it's outside the 4 or 74%, so actually I know that's what those are for percent, is 4 or 74. But I can get it for the math too. So let's go ahead and do stat, basic statistics, display. I want to get percents and the math. I want to get their ranges. So percent I know goes from a minimum of 4 to a max of 74, and now math goes from 437 to 577. So this is, got a short attention here. Was it 477? No, 437 to 577. It says, this is 437 to 577. This was 4 to 74. So here we're okay. 520 is in there, and 20% is in here. So the prediction looks good. Got a high R squared, and the values we're using for this new state, the 520 and the 20%, fall inside the ranges of the original values used to fit the model, which were 437 to 577 for the math, and 4% to 74% for the percentages. And the 520 and the 20 fall inside those ranges. So we look good here. Okay, so that is the basics of how you kind of fit a model and use it for prediction, at least using Minitab. The last thing we need to talk about is we've talked about KISS, why it kind of makes sense, but I just want to follow up on that and show you something, since we just talked about prediction too, that kind of goes along with prediction. So I'm going to scroll here to KISS versus overfitting. Remember, KISS, we want to keep things simple, right? That's sort of the idea of KISS. So in KISS, you're going to have a simple model. So for example here, the best I can do it, here's a simple regression model. Okay, it's using KISS here. The nice thing about a simple regression model, it's easy to explain, right? It's easy to explain what the terms mean. Also, as I'll show in a minute, it's actually also better for prediction than a very complex model. Here, if I wanted to, I could overfit the model. I could overfit the regression model. In other words, add a whole bunch of X terms and force the model, it's an ugly model there, I could force the model to go through every point. You can force that to happen if you have enough X terms. So R squared equals 100%. I could force that. So in other words, I could create a model here that goes through all the points. The best I can make it do that here. Kind of hard to do with this example, but you can get the idea. So it goes through every single point. So R squared equals 100%. But it's overfitted. There's no residuals. Overfitted models are bad for prediction. So for example, let's say we have a percent so let's say we have let's say 54%. Let's say 54% taking the SAT. We want to predict the SAT verbal score for the state. Well, here, so 54 is around here somewhere. Notice what we do here with the KISS. We go up here and then go across. So So it looks like it's probably best I can do it somewhere around there, right? In other words, what we're doing is we're looking kind of the average. We're looking at the average of the scores around there kind of thing and saying what value do we expect. But with the overfitted, you're looking just an extreme value. So here's 54 over here, but I just get the one value. So I get, best I can, a value down here someplace. So in other words, the KISS model takes an average. That's a bad average. Let's get a better average. Takes an average of the scores around 54, or the percents around 54, to get its prediction. So in other words, it accounts for variation. It's giving you sort of the best of the average. But the problem is, gets a little more space here, so I'll scroll a little bit. With the overfitted model, doesn't account for variations in scores or values. It only looks at the 54%, which could be an outlier for SAT verbal. And here it is it's on the low end, right? It's kind of on the low end of that group. So here visually it seems like the KISS is a much better estimate. It's kind of taking into account all those around it, or this just looking at that outlier. So that's why overfitting can be bad for prediction, and why it makes sense again to use the KISS principle rather than try and shove a whole bunch of X terms in your model to just get your R squared as high as you can. That's a bad thing to do. Keep it simple, make it explainable. You expect variation, you don't expect R squared to be 1, you expect some randomness you can't explain, but that's sort of the best model to fit.